Hello, my name is Juan Pablo Alquizer Barrera, and this project is called Personalized Grease Splint. The project focuses on the design and experimental analysis of a 3D print orthopedic splint for biomedical applications. Traditional grease splints can sometimes be uncomfortable, poorly ventilated, or difficult to customize for each patient. Because of this, the objective of the project was to develop a personalized grease splint using PLA and compare two different configurations, a solid design and a voronized design. The goal was to analyze differences in rigidity, flexibility, ventilation, and mechanical behavior. The splints were manufactured using PLA, which is a thermoplastic material commonly used in 3D printing. PLA was selected because it's lightweight, easy to print, biodegradable, and suitable for temporary external biomedical applications. After printing, the splints were heated using hot air and water, and manually molded to the anatomy of the user due to the thermoplastic behavior of the material. Two different configurations were analyzed. First one was a solid splint, which provided a higher rigidity and better structural support. The second one was a voronized splint, which includes a porous geometry to improve airflow and reduce weight. Also, the voronized model reduced the mass from approximately 120 grams to 105 grams. It also became more flexible and more susceptible to deformation. To evaluate the mechanical behavior of the splints, two experimental tests were performed. The first test was a static loading test, where a vertical load was applied while the hand remained fixed. The second test was a manual compression test simulating a gripping motion, which generated lateral deformation in the splint. Both tests helped analyze how the structures respond under different loading conditions. Deformation analysis was performed using Kinovea and GOM software. Markers were placed on important regions of the splints to track movement during the tests. Kinovea was mainly used to measure displacement between 2 points and calculate deformation values. GOM allowed visualization of deformation across different regions of the splint, although it presented some instability during tracking. The experimental results showed important differences between both configurations. The solid splint showed lower deformation values and higher rigidity, meaning it proved better mechanical support and resistance under load. In contrast, the voronized splint showed greater deformation and flexibility, but also improved ventilation and comfort. This demonstrates a balance between structural rigidity and user comfort. One of the main technical difficulties involved the deformation analysis using GOM software. Marker instability, linear variations, and subject movement caused inconsistent results during some experiments. To solve this problem, several repetitions were performed, marker positions were adjusted, and only stable video segments were selected for analysis. Another issue was the progressive wear of the Velcro straps during repeated testing. This project helped develop knowledge related to biomaterials, 3D printing, mechanical analysis, and experimental testing. It also improved problem-solving skills through repeated experimentation and correction of errors. For future improvements, the porous geometry could be redesigned manually to better control thickness and rigidity. The fastening system and internal comfort of the splint could also be improved. In conclusion, this project allowed the integration of biomaterials, 3D printing, and experimental mechanical analysis in the development of a personalized orthopedic device. The comparison between solid and voronized configurations helped understand how geometry affects rigidity, flexibility, comfort, and structural behavior in biomedical applications. Thank you for your attention.